All right, as we start off in section 7.4, it's some more Algebra 2 with factoring. And there are 3 objectives that we are going to tackle. It's objective 12, 13, and 14. 12, you're going to understand how the zeros of a polynomial relate to its factors. So we're going to relate the graph of the polynomial with the algebraic factors, which is review for you. 13, we're going to use the factor theorem and long division to factor polynomials. You also did that back in Algebra 2x. And then 14, you're going to write equations of a polynomial from its zeros, which also should be review. So if you liked doing this in Algebra 2, it's all review, and let's just again dive into these notes. The first objective of this section talks about how the zeros are related to the factors, and we're going to do this example right here to cover that objective. The expanded form of this third degree polynomial is right here. And what they want us to do is factor it, and then from there look at the factors and identify where the zeros are for the function. So to factor this one, there's a couple of ways you could start. The first thing I would encourage you to do is look for some GCFs, or a greatest common factor. And you can pull out of all 4 of these terms the factor of 2. So let's go ahead and do that. So it'll give us the 2, and it'll leave us with x cubed plus x squared minus 17x plus 15. Now, from here, the skill set in factoring, we're not quite there on what to do with it. You might want to try factor by grouping, but unfortunately that doesn't work for this case. And I'm going to give you some other techniques to do long division today. So let me just tell you, if you were to factor out this 4-term polynomial of degree 3, what you're going to get are these 3 factors here. Okay. Now, those are the factors. Once you have those, you can find the zeros of the function. And just remember this, folks, the word zeros, it means multiple things. It's the roots, it's the x-intercepts, it's the answers, it's the solutions, all of that. So all you have to do to find the zeros is this. Go in and take each of the factors and set them equal to 0. So I'm going to do 2 equal to 0, x plus 5 equal to 0, x minus 1 equals 0, and x minus 3 equals 0. Now 2 equals 0 does not make sense. 2 cannot be 0, so therefore this component here will not give us a 0 of the function. Here, though, to solve for x, just subtract 5 from both sides, so we're going to get x is negative 5. That is 1 root, or 1 0 of the function. Here, add 1 to both sides, so x is 1. And then here, add 3 to both sides, so x is 3. Now, if you were to take your graphing calculator and put this third degree polynomial in there and graph it, you're going to get something of this nature. It's just going to be a very rough sketch. Something that has an x-intercept, one is going to be at negative 5, so let's put that right here. One at a positive 1 and one at a positive 3. And I will tell you the shape of this when you draw it is going to look something of this nature, such that this function will actually cross at the 3 zeros that we found. So just know the factors and the zeros are related. When you have the factors, set them equal to 0 and solve, and you can visually see the x-intercepts or the zeros of the function. Now that last example we just looked at really summarizes the factor theorem. The factor theorem says this: if we know x minus c is a factor, then we know that if we put c into the function itself, we will get 0. And again, that just tells you, take the factor, solve it for setting it equal to 0, and you're going to get x is c. So if the value is c or 3 or 4, if you put the value you get when you find the 0 or the x-intercept, when you put that back into the function, it's going to equal 0. That's what an x-intercept means. That's what a 0 means. It means when you find the answer and then put it back into the original equation, the answer is 0. Now, some other special features here. It says here, for any polynomial p of x with real coefficients in any real number c, the following are logical equivalent statements. x minus c is considered to be a factor of the function. If that is, then we know p of c is equal to 0. Again, if the factor here was x minus 2, this would mean that p of 2 would equal 0 on the function if that were the case. C itself here, or in our case, the number 2 would be considered to be called an x-intercept of the graph. C is also called a 0 of p of x. And the remainder of p of x when it's divided by a factor. So if I take the original function and I divide it by one of its factors, the remainder is actually going to be the number 0. It will divide into the original polynomial perfectly with no remainder if it is a factor. Now, the second of 3 objectives for this section was to use the factor theorem to factor polynomials. And the factor theorem, again, just says this: if we can find the factors of a polynomial, we can take those, set them equal to 0, and we can actually get the zeros of the function. So let's go ahead and see if we can factor this 4th degree polynomial. And if we can factor it, then we can find its x-intercepts or its zeros and get a quick sketch of what it looks like. First thing, again, you might want to do is look for a greatest common factor of all 4 terms. On here, I do see one. You might want to pull out and here an x out of everything. That might help you, and it may not. And again, there's going to be a variety of ways to approach this. So let's do one factoring. I'm going to pull out a greatest common factor, which is going to leave me with this right here. Okay. If we do that, then I'm going to challenge myself to look at the 4 middle terms and see if I can factor it again. And I suspect factoring by grouping works nicely here. We can take this and factor something out, and we can also factor out of here. So let's do that. Out of the first 2 terms, I can pull an x squared out. That'll leave me with an x minus 6. From the last 2 terms, I can pull out a negative 4. That'll leave me with an x minus 6 on the inside here too. Now, what we can do within this entire long component, I can actually factor out x minus 6 from both. So if I do that, I'm going to be left with this right here. That's the original x. I'm going to pull out the x minus 6. And then what's left over is the x squared minus 4. Okay. Now the next thing you might want to do, there's actually a few options. You can continue to factor this. You can factor this down, by the way. This does factor nicely. I'm just going to write it like this. X squared minus 4, factors of negative 4 that add to 0 would be x plus 2 and x minus 2. Okay. This function is completely factored. Now, to find its zeros, all you need to do are take all the factors and set them equal to 0. So we're going to have, this is set up for 1, the second, the third, and the fourth. So when you solve, one of the zeros is x is 0. The other will be at 6. Here there's going to be one at negative 2. Here there's going to be one at positive 2. Okay. Now, let me do note, if we go back and look over up in this point right here, one thing you could have done is you could take this particular factor, set it equal to 0 and solve. If you set that equal to 0 and solve, you get plus and minus 2, which is where we would get these last 2 factors from. Now, the next thing you'd want to do is you can actually put this in your graphing calculator. If you put this in your graphing calculator, we'll be able to prove that we did find the zeros of the function. Now again, I know the zeros here happen at 0, at a 6, and we'll assume that's there. We'll put this as a 2, make this a negative 2. The shape of this function, what it's going to look like, is somewhat of this nature here. Looks roughly like that. Again, this is a 4th degree polynomial. And if you remember from Algebra 2, a 4th degree polynomial has at most 3 different turning points. Here's one turning point, a second turning point, and a third turning point. So this is kind of the maximum number of points we can see, or turns we can see for this graph. Okay. And that's how you'd go about doing this. Now I'm going to challenge you to look at this additional example and see if you can factor. Again, we have a 4th degree polynomial. This time it has 5 terms to it. might be a little trickier. See if you can figure this out with factoring, and if not, if there's another trick. So pause the video, take a look at it, and see if it's factorable first. You're going to find that this one is going to be very difficult to see how to factor, and that's the true case. So this is not a nice one. This is a little more complicated. So here's the trick, you guys. Put it in the graphing calculator. Graph this entire function here. Put this whole polynomial in the calculator. And what you're going to end up seeing is you're going to see the zeros pop out of it. And I can't put the graphing calculator on here, but you're going to have one here at -5. One's in a kind of a -3. There's going to be one at 2, and there's one at 4. And this is a 4th degree polynomial, which means it has at most 4 zeros. And in this case, it does have 4 unique zeros. So from there, I can actually back into factoring this just by graphing it. I know if these are the 4 zeros of the function, that I can get their factors. The factors are just backwards. So therefore, one of the factors has to be x plus 5. Another factor has to be x plus 3. Another is going to be x minus 2. And a last is x minus 4. Okay, those are the factors of this. So you can factor a large polynomial by graphing and check to see if you can actually see the zeros. Now part B, find all the values of x for which p of x equals 0. Well, that's basically saying find the zeros, find the roots, find the x-intercepts. We found them. Those answers are -5, -3, 2, and 4. And again, in this method, we used our calculator to help support it. Ultimately, if it's the worst case where you can't find any way to factor it, you go to your calculator, and it should hopefully tell you some visual factors. Now the last objective in this section, it says find polynomials from the known zeros. And if we look at this example here, it says find an equation for a 3rd degree polynomial, graph below. Now a 3rd degree polynomial means it's x cubed. And if you look at that, this function actually has 3 zeros. It has this one, and this. And if we look, you can assume that they are integers. This first one's at -5, this other one's at -3. And this last one's at the number 2. So it has 3 zeros. So you can go backwards and find the equation. The p of x function, or our polynomial function, has to be all the zeros written as factors. So if a 0 is -5, a factor is x plus 5. If a 0 is -3, a factor x plus 3. And a 0 is 2, a factor is x minus 2. Now, what you're going to want to do is you have to determine, though, if this function is being stretched at all, because you can tell the humps are higher than just like 1 unit high. So we have to account for some type of scale factor or a stretch, and I'm going to call that the letter A. So when you look at this, what I could easily do is multiply these 3 binomials together and get a 3rd degree polynomial. My only issue is, is there a number in there bigger than 1 that causes this graph to stretch? And this is the easy part. You just have to be careful. Look at the graph. There is something special in this graph that'll help us figure out if there's a stretch to it. And it's the y-intercept. Here we have a y-intercept at 0, -60. And what that means, folks, is the x and the y values, or the p of x value. So what you can do is you can take that y-intercept information and plug it into the graph. Fine. I'm going to put 0 or -60 in for p of x, because that's my y, and then go put 0 in for all the x's. And keep that a there. Well, when you simplify this, we're going to have 5 times 3 times -2. 5 times 3 times -2 is going to give me -30 with the a. And if you solve this for a, you would divide by -30. So a is actually equal to 2, which means there is a stretch to this graph. So what does the final equation look like? It's this. The p of x function is equal to 2 as a stretch, and then we would have the other factors with it. Now typically I would want this written in standard format, which would mean I'd want you to do all the multiplication here. But for our purposes right now, I want you to understand how to get this component together. most common mistake here is just to put the three factors together and not to consider that there's some type of stretch going on like the letter A. So just be careful with that component. Now this additional example is more practice of just the problem we looked at, except they don't have a picture of the graph. They've actually told us that we have a third degree polynomial here, it's a degree 3, and they've mentioned that they have the, they are calling them the x-intercepts here. They have 3 x-intercepts. Those are the zeros. We do have a y-intercept, by the way, at negative 624. That means it's 0, negative 624 is an ordered pair that sits on this graph. Again, that is our xy ordered pair. So go ahead, pause this video for a second and see if you can come up with the right equation for this final polynomial. Now, the final equation you should have gotten is realize there is a stretch to this graph. It's a negative 1/2 stretch, and I found it in a similar fashion. Folks, one thing you can do is if you think this is the equation, put this in the graphing calculator, and you can type it even in this non-distributed format, and check and see, do you see the x-intercepts happening here? Do you see the y-intercept happening there? You should be able to confirm that you do have the correct graph. If they had given you a picture of the graph, again, type your final answer in the calculator, change the window to match the appropriate window on the paper, and just see if you have the same graph, and you can actually check your work. Now this last problem here is again the third objective where they want us to write an equation of a polynomial given the zeros. But this one has a little twist to it, so let's just set it up. It's a third degree polynomial with integer coefficients, and here are the 3 zeros. So what I would do is, let's just get right started with it and change it around. So we're going to have p of x is equal to x minus 1, x minus 3/5, and then times x plus 2/3. Now, this is all fine and dandy, and by the way, they don't give us any information about y-intercepts or anything more about the graph, so I don't know if there's a stretch going on. I can't do much else with the stretch right now, so I just assume it's at 1. But I do have a problem with this function. If I were to do the distribution on these 3 binomials, I would not have integer coefficients as it says I have to. I have to get rid of these rational numbers or these fractions. So what we need to do is think about it in terms of this. The x minus 1 is just fine. That's already an integer. But this right here, x minus 3/5, I need to get rid of that 5 on the bottom of the fraction, basically. Easiest way to do it is just multiply this factor by 5. If I were to multiply 3, by the way, I'd have 5x minus 3. Okay. On this side here, too, x plus 2/3, I can't have the 3 for that fraction in the denominator. Again, the easiest way to get rid of it is multiply by 3. And if I were to multiply it by through, I'd get 3x plus 2. So let's go ahead and do that multiplication through. Again, this would be 5x minus 3 and 3x, fix that, sorry, 3x plus 2. Now, keep in mind, if I were to take this here and set that equal to 0 and solve, I would get negative 2/3, which is one of the zeros of the function. Okay, now what you're going to want to do is multiplication. Let's get this in standard format. I'm going to multiply these 2 binomials together first, and that's going to give us a, let's see, 5x squared, and our middle term on here is going to end up becoming a negative 8x plus 3. Now, to get this in standard format, you're going to have to come in and multiply 6 different terms, do the distribution of this trinomial with this binomial, and when you do that, you will end up getting a final third degree polynomial that looks like this guy right here. This is a sufficient answer because all of the coefficients here are integers. So the 15, negative 14, and negative 7 are good to go. Again, you could put this in the graphing calculator and just double check that the zeros happen at the 3 numbers indicated. As far as the homework goes, I think these are all good problems. If you're doing the normal assignment, you can go ahead and skip number 6. But you will get a good flavor for everything we talked about today in this assignment. Good luck.